Today we're going to present the electromyographic human-machine interface. The aim of our project is to design and implement a part of a human-machine interface system controlled by muscle activity of a user. The overall system is composed of two electrodes, which you can see on the right bottom on part of the slide. These two electrodes are placed on the surface of the skin above the muscle in order to get an input signal, which is then magnified by an instrumentation amplifier. We needed to make sure, in case of when the muscle is relaxed, that we don't have a DC offset. Then we need to build a high-pass filter. Then the signal was rectified and integrated. In the end, our prototype should indicate, using audio, visual, or motion, the movement and strength of the muscle activity. The first circuit that we have built was the instrumentation amplifier. It uses 3 out of 4 op-amps from the LMC660CN. Within the first 2 op-amps, we generated 2 input signals of amplitudes 2 millivolts and 5 millivolts respectively. Then the potential difference of these 2 signals are gonna be magnified, and we'll see the output through the third amplifier. We expect a sinusoidal waveform on the oscilloscope.
So, for the picture showing on the right-hand side, this is the result for the simulation. And the blue line is the output of the signal, and the other 2 is the 2 input signal. And we can see that the output signal has been amplified by the difference of the input signal. And the theoretical gain we calculate is about 97, and the simulation result is about 99. And for the actual circuit, we connect positive 9 volts and minus 9 volts with 30 milliamps current power supply on the circuit, showing on the first picture. And for the second picture, we can see that we use a variable resistor, so we can change the gain accordingly. And for the third circuit, for the third picture, we can see that our output produces a perfect sinusoidal signal, which means that the noise has been reduced.
An active second-order high-pass filter was used as our filter. A second-order filter was chosen as we wanted a steeper both plot. When deciding between the active and passive, both produced similar results on multisim. However, we ended up choosing the active filter as an op-amp provides a high input impedance and low output impedance, resulting in efficient transfer of signals. The schematic of our filter is shown in this slide, and based on a research we found on the International Journal of Engineering, Science and Technology, usable energy of an EGM signal is between 50 to 150 Hz. Hence, we set the cutoff frequency to 50 Hz, and doing so also theoretically allows us to eliminate the 50 Hz component from the means. By setting the capacitance as 1 microfarad and using the formula 1 on 2 pi RC, we calculated the resistance to be around 3000 Hz. This slide shows the Bode plot from the simulation when we connected when connected to the MIDAC. Both plots produce similar results, and we can confirm that our high-pass filter is working as expected. Looking at the oscilloscope, supplying the circuit with a sinusoidal input of 5 peak-to-peak voltage and a DC offset of 1 volt resulted in a sinusoidal output of 1 volt with the 1 volt offset removed, also confirming that our high-pass filter works as expected. The physical circuit and the signals on the digital oscilloscope in the lab is shown here.
So the purpose of the rectification is to convert an AC signal to DC. And in this case, the EMG signal needs to be rectified in order to calculate the running average of the amplitude. And so most diodes have a threshold voltage of 0.7 volts. And this may be a problem since the output EMG signal, even after amplification may have a value less than that of the threshold. Therefore, the rectifier circuit that we build must involve an op-amp, which is also known as a precision rectifier. And as shown on the schematic diagram on the left, we have built a full wave, and the full wave precision rectifier is pretty much involving a half wave combined with a sum amplifier. And we have also used a LM324 and quad op-amp and configured it as an inverting amplifier. And the full wave rectifier is used since the muscle movement will generate both a positive and negative EMG signal. And if the half wave is used, some information of the signal may be removed. And this is not ideal for us since the power signal of the EMG is already really low to begin with. And one advantage is of the full wave with the half wave is that its rectification efficiency is double than that of the half wave, since it converts both the cycle of AC into DC. And the ripple factor is less in full wave, and this would also result in a smoother wave output waveform. And the full wave rectifier produces a higher average DC output voltage and current, and it also result in a higher output power. And the result on the left shown is the simulated MIDAC on the MIDAC, and the output on the right is shown after we combine all the circuits with the instrument amplifier and the filter output.
This is the integrator, or known as the envelope detector. It works to smooth out the signal by attenuating the noise at the high frequency range. So essentially, the higher the input frequency of the signal, the lower the output amplitude of the signal will be. And as shown on the diagrams, those are the output of the integrator circuit from MIDAC. So as you can see, the square wave was turned into a triangular waveform, and the sine wave was turned into a cosine waveform. Below is a schematic diagram for the integrator circuit. It has a gain of -10, a cutoff frequency of 1.59 Hz. So far, we have successfully smoothed out the output signal from the rectifier on MIDAC, but the major problem we encounter is that we are unable to obtain a desired output on the oscilloscope. So what we can do afterwards is that we can add an inverting low-pass filter at the output of the integrator circuit, or we can change the cutoff frequency by choosing a different values for resistors and capacitors, or we can choose another type of operational amplifier.
There are some features that have added to the output part. The bar lamp will throw a warning message when the input is unexpectedly high or low. When the Arduino is turned on and initialized, the bar lamp will blink to show that. They will also behave differently when the problem is unexpected. In the first video, channel 1 is the input to the Arduino from the integrator, as the number of lighting LEDs also increases. I used a potentiometer in the second and third video to simulate the input and demonstrate the dimming LED, servo motor, and the speaker more intuitively. The second video shows the warning mechanism. When the input is too high, 4 yellow lights will indicate that. When it is lower than expected, 1 yellow light will tell that. The third video sweeps through the input and shows that the speaker works perfectly, not making any noise.
And this is a list of components we use for this scenario. And our group also done some additional remote tasks. For the cost of manufacturing, you can see that with the increase in quantity, our cost for one prototype has decreased. This is because the price of each component would decrease if we purchase more components at the same time. And the price we found is from the website called OEM Makers. And this is the PCB layout for our circuit, but it's not finished yet.
This slide shows the Gantt chart and the days assigned for each task.
Thank you so much for listening.